In this video, we are going to look at writing the equation of a polynomial based on certain given conditions. We saw the graphing polynomial, we talked about end behavior, we talked about roots of polynomial, we talked about y-intercept of polynomial. So today, we're going to be given some conditions and we're going to look at writing the equation for a polynomial based on the conditions that are given. Just a quick recall from the last video that if a root has odd multiplicity, it is going to cut through the x-axis at that point. If a root has an even multiplicity, it is going to touch the x-axis and bounce back in the direction it came from. So here's first example. Given the polynomial function, find its roots, their multiplicities, and y-intercept. So we are actually given the function or the equation. This is a polynomial function f of n, where independent variable is n and the dependent variable is f here. So we want to find out the roots and their multiplicities. In this case, the roots are going to be the ones that make each of these factors 0. So we can plug each of these factors equal to 0. If I plug n minus 1 equal to 0, n equals 1 will be a root. If I plug negative 15n plus 7 equal to 0 and solve for n, it would be negative 15n equals negative 7, and n would be equal to 7 over 15. And if I plug the last one, n minus 2 equal to 0, then n is equal to 2 is another root. So what is the multiplicity of n equals 1 root? The multiplicity for n equals 1 is going to be the exponent here, which is 1. So multiplicity is going to be 1 here. And for 7 over 15, the exponent is 5, so multiplicity is 5. At n equals 2, multiplicity is 3, so the exponent is 3, multiplicity would be 3. Now we also wanted to find out the y-intercept. To find the y-intercept, we can simply plug in n equal to 0 and solve this for f. So that would be f equals f of 0 when n is 0, because when we're talking about the y-intercept, it is touching the y-axis at that point. And the only way a graph can touch the y-axis is when x-coordinate is 0. So let's see, when does that happen? When n is 0, what is y value here? We wanted to find the y-intercept. So we wanted to find f of 0 here, which would be negative 3 times negative 1 times 7 to the 5th power times negative 2 to the 3rd power. And that is going to be, let's grab a calculator. It's going to be a large number. First of all, let's take care of the sign. We can have a negative times negative is a positive, and the negative number raised to the 3rd power will be a negative. So my y-intercept will be negative. I can see that. Now I'm going to go ahead and multiply 3 times 1 times 7 raised to the 5th power times 2 raised to the 3rd power. And I'm going to use calculator, and it looks like, wow, negative 40333368. That's my y-intercept. That's where the graph is going to touch the y-axis for this polynomial. Again, to find the y-intercept, we simply make the n, the independent variable, or x, equal to 0. In this case, the independent variable is n, so we simply plug 0 for n into the entire expression. Do not forget about negative 3 in the front. That is going to play a role in your leading term, leading coefficient when you open up all the, when you distribute or open all the binomials in this case. Okay, so negative 3 times negative 1 to the 1st power times 7 to the 5th power times 2 to the negative 2 to the 3rd power, and there's our y-intercept. Next, we want to write equation of a polynomial function with the given zeros and given multiplicities. So we're given the zeros and we're given the multiplicities. So 0 is 5. If 5 is a 0, then x minus 5 is a factor. And multiplicity is 1, so that would just be raised to the power 1. If 4 is a 0, that means x minus 4 is a factor, and it's going to be raised to the 2nd power because the multiplicity is 2 for this 0. And x minus 1, if negative 1 is a 0, then x plus 1 will be a factor, and it's going to be raised to the 3rd power. And there is the polynomial. No need to open the cubic bag or the square bag, it's okay to leave your answer like this. It's perfectly fine, unless the problem specifically states that write it in the expanded form. In that case, we would go ahead and use x minus 4 to the second power. We'll use distributive property, or we can use foiling in that case, and then x plus 1 to the third power. We can use the formula a plus b to the third power, or we can use distributive property and then also distribute entire polynomial. So x minus 5 is also one of the factors. Again, it's okay to leave it like that, and I'm going to leave it like this. I'm not going to open up and expand, write it in the expanded form. Next, we're given C of R is R minus 1 times R plus 3 times R minus 7. Find the coordinates of C-intercept and the R-intercept. So we know for C-intercept, the R will be 0. And in this case, if you think about, if you compare it to y of x or f of x, y is being replaced by c and x is being replaced by r. So if it was written in terms of y of x, it would have been x minus 1, x plus 3, and x minus 7, but we are writing it in terms of r. So c-intercept is going to have the x coordinate or the r coordinate as 0. So it's going to be 0 comma something, and 0 comma what? We actually need to go ahead and replace r by 0 in the entire expression. So 0 minus 1 is negative 1, 0 plus 3 is 3, 0 minus 7 is negative 7. Negative times negative is a positive number, and 7 times 3 is 21. So my c-intercept in this case is 21. We also wanted to find the r-intercept. To find the r-intercept, we will replace the c by 0. It is going to be something, comma 0. The y portion for r-intercept is going to be 0. So let's go ahead and replace c by 0. 0 equals r minus 1. R minus 1 times R plus 3 times R minus 7. Well, this is a lot of work, so I'm going to go ahead and actually, no, this is not a lot of work, because where does these become 0? This is the product of three factors. We can use the zero product property and say that this expression is going to become 0 when r is equal to 1, when r is equal to negative 3, when r is equal to positive 7, wherever each of the factors becomes 0. So there is going to be more than one c-intercept in this case, the r-intercept in this case. My r-intercepts are going to be 1, 0, negative 3, 0, and there's going to be another one, which is 7, 0. There's 3 r-intercepts, and there's only one c-intercept. So every graph of a polynomial function, if x is the independent variable, y is the dependent variable, that graph is definitely going to touch the y-axis all the times. It may or may not touch the x-axis. In case of quadratic equations, sometimes it will touch the x-axis, sometimes it won't. But it will always touch a quadratic that opens up or down. It will always touch the y-axis at some point. In case of polynomial higher order equations, we will have the polynomials depending on the roots, if they're real or not. It touches the x-axis or not. Polynomial of degree 3, p of x, has a root of multiplicity 2 at x equals 2. So p of x is equal to, the root is x equals 2, means x minus 2 is a factor, and it's going to be squared. That's what the multiplicity means. And a root of multiplicity 1 at x equals negative 4. That means x plus 4 will be a factor. So that's how we can say that it's going to be a third degree polynomial. X squared times x will be x to the third power. Now we're given some more information, which is saying the y-intercept is 0, 5. So that means there is some leading coefficient over here. I'm going to call it a. And we want to find the polynomial. So to find the polynomial, we do need to find out what's the value of a. I'm going to go ahead and use the information that y-intercept is 0, 5. So I'm going to replace the y value by 5 and the x value by 0 and solve for a. 0 minus 2 is negative 2. Negative 2 squared times 0 plus 4 is 4. So 5 equals negative 2 squared is actually going to be positive 4. So that's going to be 5 equals 16a. A turns out to be 5 over 16. So now we actually do have the polynomial we were looking for. We're going to replace a by the value of a we just found, x minus 2 squared times x plus 4. So this is the polynomial where the y-intercept is going to be 5 or 0, 5. Okay, let's see. Next example. The polynomial of degree 5 p of x has leading coefficient 1 and the roots of multiplicity 2 at x equals 4 and x equals 0 and a root of multiplicity 1 at x equals negative 3. Find the possible equation of p of x. We're not given any other conditions. We're just told that there's nothing about the y-intercept or nothing about that this polynomial passes through a certain point. We're not given any information like that. So we can go ahead and start by saying polynomial has degree 5. It has a leading coefficient of 1, which is good information. If the leading coefficient was something else, we would have to consider including that into the picture. Has a roots of multiplicity x equals, multiplicity of the root is 2, and the root is x equals 4. So x minus 4 will be a factor squared, and x equals 0 is also a root of multiplicity 2. That means I'm going to have x squared in there, or x minus 0 squared, whatever we want to call it. It's better to call it x squared because x minus 0 is still x. And a root of multiplicity 1 at x equals negative 3. If x equals negative 3 is a root, that means x plus 3 is a factor. And there's my polynomial. And how do we know it's a fifth degree? Think about multiplying all these, opening up x minus 4 squared using distributive property and multiplying. Our leading term will be a fifth degree term here. That's all for this video, and see you in the next one.